Hello, this is Professor Stephen Neshaba, and I'm here to help you out with the computational guided inquiry on intermolecular forces of atmospheric molecules. So part of the pre-lab for this activity is to look up the electronegativities of some atoms like oxygen and nitrogen that appear in atmospheric molecules, and you can do that by going to this Wikipedia page, and there are these numbers that appear here. But then what we'll be doing during the exercise is running Spartan, and you can get started on this if you bring up Spartan according to the instructions that I've given you on the Moodle page. And I just kind of want to get you started on how to do all that. So I brought up Spartan here, and in the upper left corner here is what's called the new build icon, and if you just hover over these things, you can see that there are different items that appear. So there was the new build, and other ones that we'll be using are surfaces and properties and output. So first thing we'll do is we'll go to new build, and you can see that there's various panels over here. The default is organic, and if you're going to build the water molecule, that's this guy right here. So I'm going to click on this this molecule and just click once on here. Now if you take two fingers on your scratch pad, you can make it bigger. If you left click, then you can rotate it around. These yellow nubbins here are oxygen, hydrogens, and that makes us H2O. It just defaults to that. You don't have to add them on. So one of the first things that you'll be doing, according to the exercise, is exploring different models. So there's that item up there. You can look at this as a wire model, as a ball and wire, and so on. The ball and spoke is what comes up by default. Another thing you'll be doing is to be carrying out a calculation, and that's what this item is here. So I'm going to click on this calculation here. We want an equilibrium geometry. We don't want Hartree-Fock. We want semi-empirical. And once you have those two set, then you click here on the lower right, submit. And these jobs should go pretty fast. Now you will want to save these in a particular place on your laptop. So I'm just going to call this water, and it's going to say, oh, I have submitted it. And you can wait for a moment. In this case, it's done. I'm going to say OK. And so the next thing that we'll be looking at is what's called van der Waals surface, and in order to do that, we go to this surfaces icon. I'm going to click on that. Down here, it's add, and you see density. That is the van der Waals surface density, and it'll compute it. And you got to click on it here. And when you're done, that's good, and that's what that is. Now, often you want to kind of see where the atoms are in there, so what you do is you click in the middle of that, and over here on the lower right, instead of saying solid, we'll say transparent, and that can kind of tell you where the atoms are. Okay, and let's see various other things. Later on, we'll have you look at the electrostatic potential map, and we'll do that the same way we did density, but you can see here it's electrostatic potential map. And because they kind of clash, you want to click on that one and not on that one. And so here we have that. And once again, if you want to look inside, you go to this, selecting it as transparent, and so forth. This little arrow just points to a particular place on that surface and tells you something about the value of the electrostatic map at that point. I can click off the side and get rid of that. And let's see, one other item that you'll be looking at is you'll be going to, let's see, output, not output, but properties. And you can see that water has a dipole moment of 1.74 dBs. If you want to look at that vector, then you click on there, and then it will show up. And as you can see, now we've got a vector that points from the positive parts of the molecule towards the negative ones. And that is the dipole moment vector. So I think that will kind of get you started on this activity. And so we'll stop.